Module 1, Lecture C, DataFrame Essentials. By the end of this lecture, you will be able to construct data frames from common sources such as dictionaries, lists of dicts, and NumPy arrays using Pandas 2.3.1. Inspect data frame structure and metadata to understand shape, columns, indexes, and basic statistics, and perform basic column and row operations, including selection, renaming, and simple transformations. Create data frames from dicts and lists of dicts. A simple way to build tabular data in Python is to start with a dictionary and then create a data frame from it. Each key in the dictionary becomes a column name, and the list of values for that key becomes the entries in that column. For example, a customer survey might use keys for customer IDs, drinks ordered, ratings, and loyalty status, each linked to a list of values. When this dictionary is passed to the Pandas library, it automatically arranges the keys as columns and the values as rows, and it infers the table's shape and data types. This approach is intuitive because it matches how you might naturally organize related lists of data in Python before using more advanced data tools. In data analysis, a common pattern is to work with a list of dictionaries, where each dictionary is one record and its keys are the record's attributes. This structure is especially useful for semi-structured data that comes from sources like JSON, web APIs, or log files. For instance, job postings can each be stored as a dictionary with fields such as title, company, and location. When you pass this list into a data analysis library like Pandas, each dictionary becomes a row, and the keys across all records form the columns. Any missing fields simply show up as missing values, which you can clean up later, making it an efficient way to turn messy data into a structured table. Using dictionaries and lists of dictionaries with Pandas shows how it can align data, handle missing values, and infer data types even when the input is messy. In research, this might come from survey responses stored as dictionaries, and in business, it might be event data where each event is a dictionary. The DataFrame constructor turns this raw Python data into a table of rows and columns, automatically detecting types like numbers and dates while preserving your original labels as column names. This creates a smooth bridge from basic Python data structures to Pandas tools for sorting, filtering, visualizing, and exploring data. Python code from dicts and lists of dicts. This section focuses on creating data frames from dictionaries and from lists of dictionaries, and on understanding how the structure of the input maps to the resulting table. You will see that dictionary keys become the column labels in the data frame. By printing small data frames, you can clearly observe how rows and columns are formed, and how missing values appear when some keys are absent in certain entries. The goal is to build intuition for how different dictionary-based inputs translate into tabular data. We begin by importing the Pandas library, a key tool in Python for working with data. Pandas lets us handle structured data efficiently, using objects similar to tables in a database or spreadsheet. By bringing this library into our program, we unlock powerful features for organizing, manipulating, and analyzing data. We create a dictionary called survey data with 3 entries, Customer ID, drink, and rating. Each entry is linked to a list where customer ID holds integers for each customer, drink holds the type of drink they ordered, and rating holds the integer score they gave that drink. This structure is designed so it can be easily turned into a data frame, with each entry becoming a column and each position in the lists forming a row of survey results. Using the Pandas library, we can build a data frame by passing in a dictionary of data. In this dictionary, each key becomes a column name, and each associated list becomes the column's values, forming the rows. This method makes it straightforward to turn structured data into a table that we can then analyze and manipulate efficiently. We begin by printing a short message to explain that we are about to show a data frame created from a dictionary of lists, so the listener understands where the data comes from. Then we display the data frame itself, which was built so that each dictionary key becomes a column label, and each list under that key becomes the data for that column. This visual check lets us confirm that the information is correctly arranged into rows and columns, and that the data frame structure matches our expectations. We create a list called orders list that holds 3 dictionaries, each one describing a single order. The first order has an ID of 1, with a burger priced at $9.5. The second order has an ID of 2, with fries priced at $3. The third order has an ID of 3, with a soda priced at $1.5 and an extra field for size in ounces set to 12. Organizing the data this way makes it easy to turn the list into a data frame, where each dictionary becomes a row and each key becomes a column. We create a data frame in Pandas from a list of dictionaries called the orders list. Each dictionary represents one row, and its keys become the column names. This lets us turn structured data into a clear table format. Once in a data frame, the data is much easier to analyze and manipulate. The code first prints a short message to let the user know that the next output will be a data table created from a list of dictionaries. It then displays the data frame that was built from that list. In this table, each dictionary becomes a row. The dictionary keys become the column names, and the corresponding values fill in the cells. This helps the user see how the original list of dictionaries is represented in a structured, tabular format. This script shows 2 common ways to create data frames with the Pandas library. First, it builds a data frame from a dictionary where each key is a column name and each value is a list of entries, producing columns for customer ID, drink, and rating. Then it creates another data frame from a list of dictionaries where each dictionary represents a row with fields such as order ID, item, price in dollars, and sometimes size in ounces. When you run the code, you see both data frames printed, and any missing information in the input appears as missing values in the resulting tables. From NumPy arrays. In scientific computing, you often move from raw NumPy arrays to a more readable tabular format. A data frame provides this by adding labels to the rows and columns of a 2-dimensional array, so each column represents a variable and each row represents an observation. Converting a NumPy array into a data frame turns a plain numerical matrix into a labeled grid. This makes data from simulations or machine learning workflows easier to understand, work with, and analyze. Think of your data as a 2-dimensional array where each row is a patient and each column is a measurement, like age or cholesterol. By itself, this array is just numbers, and you have to remember which column represents which measurement. A Pandas DataFrame solves this by letting you label columns with names such as age and cholesterol, and rows with identifiers like patient IDs. With these labels, you can select and compare values using meaningful names instead of raw index positions, which makes analysis easier and reduces mistakes. Combining multiple NumPy arrays into a single data frame is useful when the data belongs together, such as temperatures, humidity, and air quality measured on the same days. By merging these arrays and labeling the columns, you align each day's values across all variables in one organized structure. This unified data frame then becomes the main place for analysis, making it easier to filter data, compute statistics, and prepare information for visualization or modeling. Moving from separate arrays to a data frame improves organization and interpretability, and makes the data ready for analysis. Python code from NumPy arrays. This section focuses on building simple data tables from basic NumPy arrays and then making them easier to understand by adding clear labels. You will see how column labels can be used to describe what each measurement represents, so the data is immediately interpretable. You will also learn how row labels can be chosen to represent meaningful identifiers for each observation, making it easier to track and reference individual records. Together, these practices turn raw arrays into well-structured, readable data frames. We begin by importing NumPy, a library that efficiently handles numerical arrays and makes it easier to work with large datasets. We also import Pandas, a library designed for data manipulation and analysis. Pandas provides the data frame structure, which organizes data in a table-like form. This tabular format helps us manage, analyze, and visualize data more effectively. We begin by creating a NumPy array that stores patient data, where each of the 3 rows represents one patient and contains their age, systolic blood pressure, and cholesterol level. We then create a second NumPy array that holds unique patient identifiers labeled P001, P002, and P003. These identifiers will later serve as row labels in a data frame, so that each set of measurements can be clearly linked to the correct patient. We begin by defining column labels for our data frame that describe the type of data in each column, such as age in years, systolic blood pressure in millimeters of mercury, and cholesterol in milligrams per deciliter. Then we convert the patient IDs from a NumPy array into a standard list. This list of IDs is used as row labels in the data frame so that each observation has a clear and meaningful identifier. We create a Pandas data frame from a NumPy array of patient data and give it meaningful labels for both rows and columns. Each row is labeled with a patient ID so we can easily identify individual observations. The columns use descriptive names such as age in years, systolic blood pressure in millimeters of mercury, and cholesterol in milligrams per deciliter. This structure makes the patient information clearly organized and easy to access by either patient ID or measurement type. The code starts by printing a message that describes the shape and contents of a NumPy array. This message tells the user how many dimensions the array has and what they represent. In this example, the array holds data for 3 patients. The shape function is used to get these dimensions, and the printed message explains that they correspond to the number of patients and the data points recorded for each one. The code first prints a message explaining that the data frame has labels for both its rows and columns, setting up what you are about to see. It then displays the data frame itself, where each row is labeled with a patient identifier, and each column represents a type of measurement. This structured view makes it clear how the data is organized and helps you quickly interpret the information available for each patient. This script shows how to build a Pandas data frame from a NumPy array and label both its rows and columns for clarity. The array holds data for 3 patients, each with 3 measurements: age, systolic blood pressure, and cholesterol level. Patient identifiers are assigned as row labels, and descriptive names are used for the measurement columns. When run, the script prints the shape of the array to confirm it contains data for 3 patients, then displays the labeled data frame so the information is easy to read and analyze. Index and column labels. When you create a data frame in Pandas, you are not only storing raw data, but also assigning labels that give the data meaning. These labels include the row index and the column names. By default, Pandas uses simple integer indexes and basic column names, which may work for quick tests, but are not ideal for serious analysis. In a real dataset, such as daily sales, it is better to label rows with dates and use clear column names like product and revenue, so the data frame is easier to understand and work with. When creating a data frame, you should be intentional about how you label the index and columns, especially when data comes from different sources. With a dictionary, the keys become column names, so clear and consistent labels help later analysis. With a list of dictionaries, each dictionary is a row. Missing keys produce missing values, and the columns come from all keys that appear. With a NumPy array, there are no built-in labels, so you need to define column names and possibly a custom index from the start. For instance, naming sensor data columns as temperature, humidity, and pressure, and using timestamps as the index makes the data frame more intuitive and easier to work with. Thoughtful index and column labels make your data analysis clearer and more reliable. A good index works like a primary key, so you can align and merge multiple data sets without confusion, such as when using patient IDs or shipment numbers. Descriptive column names embed meaning directly in the data, so you do not have to constantly check separate documentation. By choosing these labels when you first create your data structures, you turn raw values into a well-organized format that supports more complex analysis with fewer errors. Python code, index and column labels. This section explains how data frames handle row and column labels. It first shows the default index and column labels that appear when you create a simple data frame without specifying anything. Then it demonstrates how to replace the default index with custom, meaningful row identifiers. Finally, it shows how to assign custom column labels so the data becomes clearer and more self-documenting. We begin by importing Pandas and NumPy to prepare our Python environment for data work. Pandas is used for manipulating and analyzing structured data, such as tables. NumPy provides efficient numerical tools, especially for working with arrays, matrices, and related mathematical operations. Together, these libraries give us a strong foundation for creating, organizing, and processing data in a structured way in the rest of the code. We begin by creating a dictionary that stores two pieces of information: product names and their revenue in dollars. The product list includes widget and gadget, and the revenue list includes their corresponding values of $1,200 and $950. We then pass this dictionary into the Pandas library to create a data frame called df default. Because we do not specify any custom index, Pandas automatically assigns default integer row labels. This structure gives us a simple, tabular format that is easy to manage and analyze using the default indexing. We begin by announcing that we will display the default index and column labels of a data frame to set the context. Then we show the data frame that was created earlier from a dictionary, which automatically uses integer values as row indices and the dictionary keys as column names. Viewing this output lets us clearly see how Pandas assigns these default labels when no custom indices or column names are provided. We create a list of order identifiers and use it to set a custom index for a new Pandas data frame built from an existing data dictionary. Instead of relying on the default numeric index, we assign these order identifiers as the index values. This makes each row directly associated with a specific order, so the data frame becomes more descriptive. As a result, it is easier to interpret and use in the context of tracking orders. We first add a blank line to keep the output easy to read. Then show a short message to explain that we are about to display custom index labels. After that, we print the data frame using these custom labels instead of the default integer positions. This makes the row identifiers more meaningful and improve the readability and context of the data. In this example, we create a 2x2 numerical array using NumPy, where each entry is a measurement. The first row contains the values 72.5 and 45, and the second row contains 68 and 55.5. At this stage, the array is just raw data without labels. Later, we can add context, such as column names or index labels, to make the data easier to interpret. We label the data frame columns as temperature in Fahrenheit and humidity in percent, so it is clear what each value represents. We then label the rows as basement sensor and attic sensor to show where each measurement was taken. Using these labels with the NumPy array data, we create a data frame that clearly indicates both the type of each measurement and its location. This makes the resulting table self-explanatory and easy to interpret. We first print a blank line followed by the phrase labeled sensor readings to clearly separate this output from others. Then we display the data frame that holds the sensor data. This data frame has labeled columns for temperature and humidity, and custom index labels that describe each sensor location, such as basement or attic. Showing the data frame in this labeled form gives a clear, readable view of the sensor readings with meaningful context. This script shows how to use Pandas data frames with both default and custom labels for rows and columns. It first builds a data frame from a dictionary using the standard integer index and column names. Then it replaces the default row numbers with more meaningful order identifiers. Finally, it creates another data frame from a NumPy array, assigning clear column labels for temperature and humidity, and custom row labels for different sensor locations. 3 outputs let you compare default indexing with more descriptive labels that improve clarity and context in the data. Inspecting DataFrame structure. Previewing DataFrames. When you first create or load a data frame, it is important to quickly preview it to understand its structure. This snapshot of rows and columns helps you confirm that data types and formats look correct, such as dates and numeric values. By doing this initial check, you can verify that the data loaded properly, that no columns are missing, and that there are no obvious errors. This simple step acts as an early safeguard against subtle data issues that might otherwise be missed. Previewing a data frame by looking at its first few rows is important because it connects the abstract idea of the structure to the real data you are working with. It lets you quickly check index labels, how many columns there are, and what data types each column uses. This makes it easier to notice problems, such as numeric values stored as text, unexpected symbols in codes, or missing and unusual entries. By doing this regularly, you can spot patterns and data issues early, which improves the reliability of your analysis. Previewing a data frame helps you check whether its structure matches the questions you want to answer. For example, with energy consumption data, a quick look can confirm that each row is a city on a specific date with columns for consumption and temperature, which fits time series analysis. With survey data, you can see whether each row is a single response or if there are duplicates. By aligning your mental model with how the data is actually organized, you reduce the risk of misinterpreting your results. Python code, previewing data frames. This section shows how to quickly preview a data frame using simple customer order data. By using tools that display the first few rows and the last few rows, you can see a small sample of the dataset. This helps you visually check that the columns, values, and index are formatted as expected before doing deeper analysis. We begin by importing Pandas, a powerful library used for data manipulation and analysis. This allows us to work with data frames, which are key for handling structured data efficiently. By adding Pandas to our script, we unlock many tools for processing, organizing, and exploring data in a flexible and convenient way. We create a dictionary called orders data to store information about customer orders from an online store. It has 4 parts: an order ID for each purchase, the customer name, the date of the order given as year, month, and day, and the total amount spent as a decimal number. Each part is stored as a list so that all orders line up across these lists. This structured dictionary will then be used to build a data frame for analyzing and previewing the order data. We use the Pandas library to create a data frame from a dictionary called orders data that holds customer order information. Pandas converts this dictionary into a table-like structure that is easier to work with. The resulting data frame, named Orders Data Frame, organizes the information into columns for order IDs, customer names, order dates, and total dollar amounts, with each value properly aligned in rows. To quickly inspect a data frame, we first note that we are previewing its first few rows to set the context. We then call the Pandas head method with 3 as the argument to retrieve the first 3 rows. This gives us a quick visual check of the initial entries and helps confirm that the data is structured and formatted as expected. To quickly inspect the end of a data frame, you can use the tail method with an argument of 2 to return the last 2 rows. This lets you verify how the data and index look near the bottom of the table. A print statement can then show a short label, followed by these final rows, giving a clear view of the data frame's ending entries. To quickly understand the size of a data frame, you can use its shape attribute. This gives you a pair of numbers that represent how many rows and how many columns the data contains. By checking this, you can immediately see the overall dimensions of your dataset. It also helps you relate the few rows you preview to the full structure of all the data. This script shows how to quickly preview a Pandas DataFrame using a small customer orders dataset. It first displays the top few rows so you can inspect the structure and sample values. Then it shows the last rows to check the data at the end and see how the index is behaving. Finally, it prints the overall shape of the data frame, giving the total number of rows and columns. Together, these steps help you visually confirm that the columns, values, and indices are formatted as expected. Info and describe in 2.3.1. When exploring a data frame, a key method provides a quick structural summary of the data. It reports how many rows and columns there are, the column names, the data types, and how many non-missing values each column has. This is especially useful when loading data from sources like CSV files or APIs, because it lets you immediately see whether columns are treated as numbers or text, and whether important fields have missing entries. Using this overview early helps you spot data type problems and missing data before moving on to more complex analysis. Beyond looking at the structure of a data frame, you can use a descriptive statistics method to quickly summarize numeric or aggregatable columns. It reports key metrics such as how many non-missing values there are, the average, the minimum and maximum, and several percentiles. This gives you a fast view of the data distribution without needing visualizations, such as typical values and possible outliers in ride-sharing trip distances. Such a snapshot is especially useful in areas like finance or environmental monitoring to spot variables that may need deeper analysis or data cleaning. In the latest library version, you can use 2 methods to quickly understand your data. The structural summary shows whether your data frame is wide or narrow, which columns are sparse or dense, and how much memory it uses, which matters for large data sets. The descriptive summary reveals patterns and anomalies, such as unusual age values or highly variable sales that may indicate outliers. By checking these summaries regularly, you build a clear mental model of your dataset and make better choices about cleaning, feature engineering, and analysis. Python code, .info, and .describe in 2.3.1. Use the info method in Pandas version 2.3.1 to get a structural summary of a data frame, including its columns, data types, and non-missing values. Then use the describe method to produce a statistical summary of the numeric columns, such as counts, averages, and ranges. By comparing these 2 summaries, you can understand both how the data is organized and how the numeric values are distributed. We begin by importing the Pandas library, a key tool for working with data in table form. Pandas is widely used in data science and machine learning because it makes it easy to manipulate, analyze, and clean data. In this script, we rely on Pandas to create and manage a data frame so we can explore the dataset and summarize its contents efficiently. We create a dictionary to store car trip records, where each key represents one aspect of the trip. One list holds the miles driven for each trip. Another list stores the trip duration in minutes. A third list records the fare in US dollars, and a fourth list contains the driver identifiers. Each position across these lists corresponds to a single trip. This structure organizes the raw trip information so it can be easily converted into a data frame for analysis. We build a data frame from a dictionary called trips data that stores information about car trips. This dictionary includes values such as miles driven, trip duration in minutes, fare amounts in dollars, and driver IDs. When we pass this dictionary into the Pandas DataFrame constructor, it arranges the information into a clear table. This tabular format makes the trip data easier to view, analyze, and work with for further operations. We begin by printing a short message to indicate that we are about to show a structural summary of the data frame. Then, we call its information method. This method produces a concise overview of the data frame, including the column names, the data type of each column, and how many values in each column are not missing. By reviewing this summary, we can quickly understand the layout of the data and how complete it is before doing further analysis. The code adds a blank line and a short message before starting the statistical summary, so it is clearly separated from the structural summary. This visual break organizes the output and makes it easier to read. When reviewing results, you can quickly see where the structural information ends and the statistical information begins. The describe method in Pandas creates a quick statistical summary of the numeric columns in a data table. It reports key values such as the mean, standard deviation, minimum, maximum, and the main quartiles. This summary gives an overview of how the data is distributed and what typical values look like. Using it helps you quickly understand the range and central tendency of the numeric data in the data frame. This script builds a small data table of car trips with miles driven, trip duration, fare amount, and driver IDs, then uses two Pandas summary tools to understand it. The structural summary method reports each column's name, data type, and how many values are present, so you can quickly assess the layout and completeness of the data. The statistical summary method focuses on the numeric columns and reports measures like the mean, standard deviation, and range, revealing how the values are distributed. Together, these two summaries give you both a structural and numerical view of the dataset. Index and columns. In a data frame, the columns label each data field, such as customer names or transaction amounts, and the index labels each row, like line numbers in a spreadsheet. Together, they define the structure of the data and make it possible to locate specific values. This structure is essential for tasks such as selecting subsets of data or merging multiple data frames. Understanding how the index and columns work together is key to effective data manipulation in Pandas. When you first explore a new dataset, begin by looking at its index and columns because they contain key information about how the data is organized. The columns show which variables are available and in what order, such as patient ID, age, or diagnosis in a public health dataset. The index identifies each row, and it might be a simple sequence or something meaningful like dates or product IDs. Understanding these parts early helps you quickly grasp the structure of the data and organize your analysis more effectively. Thoughtful design of your DataFrames index and columns is crucial for clear and efficient analysis. A good index makes operations like time-based slicing and aligning records faster because Pandas can use the labels directly. Consistent, descriptive column names reduce errors during tasks such as aggregations and joins, especially when working in a team. By refining the index and column names early, you improve both the robustness and readability of your analysis. Python code, index, and columns. We will explore how a data frame uses its index to organize rows in a clear and meaningful way, and how column labels describe the content of each field. You will see how these labels make it easier to understand and work with the data. Finally, we will look at how to inspect and customize both the index and the column labels so the data frame structure matches your needs. We begin by importing the Pandas library so we can work with structured data efficiently. This library is essential for creating and managing data tables called DataFrames. Once imported, Pandas provides powerful tools for data manipulation and analysis that we will use throughout the script. We begin by building a dictionary called shipments data that will later be turned into a data frame. This dictionary has 3 entries, one for shipment identifiers, one for the origin city of each shipment, and one for the shipment weight in pounds. Each entry is linked to a list, so we have a list of integer IDs, a list of city names, and a list of integer weights. This structure organizes the raw shipment information into columns that can be directly used to create a data frame with the default integer index. We use the Pandas library to create a data frame from a dictionary called shipments data, which stores information about shipments. In this dictionary, each key becomes a column name, and each list of values becomes the rows for that column. Organizing the data this way turns it into a clear table, making it easier to manage, analyze, and manipulate using Pandas data handling tools. When we create a data frame, it starts with a default index that simply numbers the rows beginning at 0, which shows how the rows are initially arranged. The column labels are also set by default, based on the keys from the dictionary used to build the data frame. Looking at this default index and these column labels helps us understand how the data is structured and how each field is identified. We set the shipment identifier column as the index of the data frame so that each row is labeled by its shipment ID instead of a default number. This makes the row labels directly tied to the shipment they represent. As a result, the data becomes easier to read and understand. It also allows for more intuitive data manipulation and retrieval based on shipment IDs. The code shows a preview of the data frame after setting the shipment ID as the index. Each row is now labeled by its shipment ID, which makes it easier to identify and access specific shipments. Viewing this indexed data frame lets you quickly confirm that the data is organized in a meaningful way, with shipment ID used as the main reference for each row. We rename the columns of the data frame to make them clearer and more consistent. Using a rename operation with a dictionary, we map each old column name to a new one. For example, origin city becomes origin city name, and weight in pounds becomes weight LB. These more descriptive names follow a consistent naming style, which improves readability and makes the data easier to understand and work with. The code first prints a message saying it will show the renamed columns. It then turns the DataFrames column names into a list and prints that list. This allows you to quickly confirm that the columns were renamed as intended and see the current set of column labels in the DataFrame. This material explains how to manage and customize DataFrame indexes and columns in Pandas. It starts with shipment data that uses the default integer index, then shows how Pandas labels rows and columns by default. The shipment ID is then set as the index to give each row a more meaningful label. Finally, the column names are renamed to be clearer and more standardized, such as changing origin city to origin city name and weight pounds to weight pounds abbreviated as pounds, improving clarity and consistency in how the data is represented. Core DataFrame operations. Selecting DataFrame subsets. When working with a DataFrame, an important step is narrowing your focus to only the rows and columns that relate to your specific question. A DataFrame is like a labeled grid, and selecting a subset means choosing certain row and column labels or positions. For example, from hospital records, you might keep only the age and diagnosis columns and only the rows for patients admitted last month. This creates a simpler, more targeted view that makes it easier to spot patterns and prepare for deeper analysis. When selecting parts of a data frame, you can work either by labels or by positions. Label-based selection uses column names and row index values, which is helpful when those labels carry meaning, such as dates or IDs. Position-based selection uses integer locations for rows and columns, which is useful when exploring new data or working with a standard layout. In practice, analysts switch between these approaches, using labels when they care about semantic meaning, and positions when they need relative locations or want code that works across many different data frames. When working with data frames, you often filter rows based on conditions, such as keeping only records where revenue is above a threshold or temperature is below freezing with a valid sensor status. The data frame checks these conditions for each row and returns only the rows that meet your criteria. You can also combine several conditions, like region, time period, and product category, to refine your selection. This is essential for tasks such as spotting fraudulent transactions or focusing survey data on a specific demographic. By mastering these filtering techniques, you control which parts of the data frame enter your analysis, leading to cleaner workflows and more reliable insights. Python code. Selecting DataFrame subsets. This section shows how to work with parts of a data frame by selecting subsets using both labels and numeric positions. You will see how to pick specific columns, as well as how to filter rows based on simple conditions. The focus is on clear, basic examples, so beginners can read and understand the output easily. By the end, you should be comfortable choosing only the data you need from a larger table. We begin by importing the Pandas library so we can work with data in table form. This gives us access to data frames, which are the main structures we will use to store and manipulate our data. By bringing pandas into our environment, we can efficiently handle, analyze, and transform structured data throughout the script. We create a dictionary called data to store information about hospital patients, where each entry represents one attribute, such as patient ID, age in years, diagnosis, and number of nights stayed. Each attribute is linked to a list of values, and each position in the lists corresponds to the same patient across all attributes. For instance, one list holds all patient IDs, another holds their ages, another their diagnoses, and another their lengths of stay. This organized structure lets us easily convert the information into a data frame, which makes it simpler to work with and analyze the patient data. We use pandas to create a data frame, which organizes our information into a table. The data is first stored in a dictionary, where each key is a column name and each value is a list of entries for that column. When we pass this dictionary to the data frame constructor, it becomes a structured table. This tabular format makes it easy to manipulate the data and perform analysis efficiently. We start by printing a short message to explain that we are about to show the entire data frame, which sets the context for what follows. Then we use the print function to display all of the data, including every column and row. Seeing the full data frame is important because it gives us a complete view of the data set and helps us understand its structure. With this overview, it becomes easier to decide how we might manipulate or analyze the data next. We begin by selecting a subset of columns from the data frame using bracket notation, choosing only the columns labeled age, years, and diagnosis. This selection creates a new data frame that contains just these two columns from the original data. We then print this smaller data frame so we can quickly check that the correct columns were extracted and that the operation worked as intended. We use the loc accessor in Pandas to select specific rows and columns based on their labels rather than their numeric positions. In this example, we choose the rows labeled from 101 through 103, including both endpoints. From those rows, we keep only the columns named patient ID and stay nights. This gives us a focused subset of the data, and we then print it to the console to check that we selected the correct information. Using the Pandas library, we can select specific rows and columns from a data frame based on their integer positions. We do this with the iloc accessor, which lets us specify the row and column indices we want. In this example, we choose the first two rows and the second and third columns, creating a smaller data frame that contains only that subset. We then print this subset to display just those selected rows and columns. We filter the data frame to keep only rows where the patient is older than 40, and the hospital stay lasts at least 3 nights, using a logical AND condition to combine these two requirements. The filtered result is saved in a separate subset. We then print a brief message explaining that we are showing rows that meet these conditions, and finally display the filtered data frame so we can see which records match the specified criteria. This script shows how to select and filter data from a Pandas data frame using both labels and positions. It starts with a table of patient information, then selects only certain columns, such as ages and diagnoses. It demonstrates using the label-based selection method to choose specific rows and columns, like patient IDs and number of nights stayed, and the position-based selection method to get ages and diagnoses for the first 2 patients. Finally, it applies conditional filtering to keep only patients older than 40 who stayed at least 3 nights, illustrating key ways to manipulate and narrow down data in Pandas. Safe column renaming. Renaming columns in a data frame is important because these names are how you and your team interact with the data. Clear, consistent column names make it easier to select data, apply transformations, and understand results, while unclear or cryptic names can lead to confusion and mistakes. Real datasets often use names with spaces or abbreviations that are not intuitive, so changing them to more descriptive labels improves readability and reduces mental effort. It is also important to rename columns in a careful, explicit way so that the changes are reversible and do not cause data to be lost or misaligned. When renaming columns in a dataset, always refer to them by their original names rather than by their position. Column order can change over time, especially in evolving datasets like monthly reports, and relying on position can easily cause errors if new columns are added. To avoid mistakes, clearly specify which columns you are changing, what their new names are, and verify that those original columns actually exist. This practice is especially important in collaborative work because it helps everyone share a consistent understanding of the data structure. When renaming columns, keep names consistent and think about how changes will affect future work and downstream systems. Use a clear naming convention, such as lowercase with underscores, and apply it across all datasets so joins and dashboards work smoothly. In projects that combine multiple data sources, aligning key variables under a shared naming style makes merging easier and reduces errors. Always document any renaming so others can understand what changed and why, which improves transparency and strengthens your data pipelines. Python code, safe column renaming. Use explicit name mapping when renaming columns so that each old name is clearly matched to its new name. Avoid relying on the position of columns, because positional assumptions can silently break your renaming logic if the order changes. Aim for consistent, reversible column names so you can reliably track, audit, and repeat your analysis. The script starts by importing the Pandas library, which is necessary for working with tabular data in the form of DataFrames. This import gives the code access to powerful tools for creating, modifying, and analyzing structured datasets. With Pandas, the script can perform tasks such as building data frames and renaming columns. Overall, importing Pandas is a foundational step that enables all the later data handling operations in the code. We begin by building a dictionary that represents a small marketing dataset, where each key is a short column name like patient ID, admission date, and primary diagnosis code. Each of these keys is linked to a list of values, such as all the patient identifiers or all the admission dates. Organizing the data this way prepares it to be converted into a data frame so we can work with it in a clear, structured table format. We begin by using the Pandas library to create a data frame, which organizes our initial marketing dataset into a clear table. This table includes columns with somewhat cryptic names that represent information like patient ID, admission date, and primary diagnosis. Structuring the data in this way makes it much easier to work with, so we can efficiently manipulate and analyze it in later steps. We begin by printing the original column names of the data frame to establish a clear baseline before any renaming. Seeing this initial list lets us understand the current structure of the data. After we rename columns, we can compare the new names to this original list to confirm that the changes were applied correctly. This also helps ensure that no unexpected or unintended modifications were made during the renaming process. We create a dictionary called the rename map to convert old column names into clearer, more descriptive ones. Each original column name is paired with a new name that better explains the data it contains. For instance, a short or cryptic label for patient identification becomes patient ID. A date of admission label becomes admission date, and a diagnosis label becomes primary diagnosis. Using this explicit mapping makes the renaming process clear and avoids confusion that could occur if we relied only on column positions. We rename the columns of the original data frame using a predefined mapping dictionary and the Pandas rename method. In this mapping, each old column name is explicitly paired with a new, more descriptive name. Because the renaming is based on these name pairs rather than column positions, it does not depend on the order of columns and remains reliable even if the dataset structure changes. This approach improves both the readability and long-term maintainability of the data analysis. After safely renaming the columns in the data frame, we display the list of column names to verify that the changes were applied correctly. This confirmation step ensures the new names are accurate and clear. It also serves as simple documentation for future work, helping maintain consistency and reliability in later data analysis. We are working with a new version of a dataset where a column has been added at the beginning, changing the column order. The data is stored as a dictionary, whose keys are the column names. The first column is campaign ID for campaign identifiers, followed by patient ID for patient identifiers, then admission date, and finally, a primary diagnosis code. This structure will be used to show how changing column order can affect how we rename columns. Using the Pandas library, we create a new data frame from a dictionary called Data New. In this dictionary, each key represents a column name, and each value is a list of entries for that column. When we pass this dictionary to the data frame constructor, Pandas converts it into a structured table. The result is an organized set of rows and columns that is ready for further data manipulation or analysis. The code starts by creating a list of column names from a data frame, then uses this list in a flawed way by assuming that the second column always contains the patient identifier. This approach is dangerous because it depends on the column's position instead of its actual name. If the order of columns changes in future datasets, this assumption can easily break the code and lead to incorrect results. A more reliable method is to reference columns by their names rather than their positions. This line of code tries to rename the second column of a data table by assigning a new name based only on its position. It assumes the second column is always the patient identifier and that the column order never changes. If the order does change, the wrong column may be renamed because the code does not check the actual column name. This is risky, since it can fail silently and lead to incorrect data handling without any obvious warning. We create a new data frame by copying the original one so we can safely experiment with renaming its columns. This copied version is stored in a separate variable and acts as a sandbox for changes. This code replaces the data frame's column names with a new list of names, assuming the columns appear in the same order as the list. That assumption is risky because if the data frame structure or column order changes, the wrong names may be assigned. This example shows how renaming columns by their position instead of using an explicit name mapping can quietly introduce bugs when the column order is not guaranteed to stay the same. We create a dictionary that maps original column names to new, more descriptive names and use it as a clear guide for renaming columns in a data table. By using the original names as the keys, the renaming process does not depend on the order of the columns. This makes the code more robust to changes in the dataset's structure and helps keep the analysis reliable and easy to understand. We rename data frame columns by using a mapping from old names to new names. This method does not depend on the order of the columns, which is important when the dataset structure can change over time. By matching names directly, we keep the renaming process consistent and reduce errors that might occur if we relied on column positions. The example compares two ways of renaming data frame columns. In the first case, columns are renamed by assuming a fixed position, which leads to incorrect names when the dataset structure changes. In the second case, columns are renamed using a mapping from original names to new names, which works correctly even if the order changes. This contrast shows that relying on column order is fragile, while using explicit name mappings is a safer and more reliable approach. We print the column names of the data frame after renaming them using an explicit name mapping. By checking these printed names, we confirm that each column was renamed correctly. This verification does not depend on the original column order. As a result, we can trust that the renaming is accurate and reliable for later data analysis. This script shows why you should rename columns in a Pandas DataFrame using an explicit mapping from old names to new names. It starts with a small dataset that has unclear column names and safely renames them with a dictionary, making the changes clear and reversible. It then adds a new column and demonstrates how renaming columns based on their position can fail when the column order changes. By contrasting the correct result from name-based renaming with the incorrect result from position-based renaming, it emphasizes that you should avoid relying on column order and instead use explicit name mappings for consistent, reliable data analysis. Column transformations. After you can select and rename columns, the next step is to transform them so the data becomes useful for analysis. This includes cleaning existing columns, such as turning text-based prices into numeric values or standardizing capitalization in product categories. You can also create new columns, for example, by calculating revenue from quantity and unit price, or computing age from a birth date. These kinds of transformations turn raw data into features that are ready for analysis or modeling. When transforming columns in a dataset, you apply functions to each value to clean or change the data so it better fits your analysis needs. This might include trimming spaces, converting text to numbers, expanding abbreviations in job titles, or changing miles to kilometers. You can also combine or derive columns, such as merging first and last names or calculating profit margins. Overall, these transformations reshape the data so it can more effectively answer your questions. In real-world datasets, it is essential to clean and transform data so it becomes consistent and ready for analysis. Missing values, such as temperatures, might be filled with a regional average or marked for later review. In financial data, you may clip extreme outliers or normalize values to handle errors and differences in scale. For survey responses, converting satisfaction levels into numbers makes them easier to analyze. Together, these steps reduce noise and inconsistency, producing clear, reliable columns for further work. Python code, column transformations. In this lesson, you will work with a small Pandas data table to practice basic column transformations. You will see how to clean text values, change column data types, and build new columns based on simple calculations. The focus is on keeping everything beginner-friendly so you can easily follow along. All examples are designed to run smoothly in a Colab notebook, making it simple to experiment and learn by doing. We begin by importing the Pandas library, which is a key tool for working with data in table-like form. Pandas lets us create and manage data structures called DataFrames that resemble database tables or Excel sheets. In this script, we use Pandas to transform the data frame by cleaning text, converting data types, and computing new columns. Overall, Pandas provides the core functionality needed for our data analysis and manipulation tasks. We begin by setting up a small dataset stored in a dictionary that will later become a data frame. It has 4 columns, item names with different capitalizations of the word laptop, category labels with variations of the word electronics, quantities as integers showing how many items were ordered, and unit prices stored as text values in dollars. This structure intentionally mixes inconsistent text and numeric values saved as strings so we can later practice cleaning and transforming the data using Pandas. We build a data frame from a dictionary called data that stores information about items, their categories, quantities, and unit prices. Using the Pandas library to create this data frame organizes the information into a clear, table-like structure. This makes it much easier to work with the data, perform calculations, and carry out further analysis in later steps. We clean the category column in our data to make all category names consistent. To do this, we first remove any extra spaces at the beginning or end of each entry, then convert all the text to lowercase. The cleaned result is saved in a new column called Category Clean. This gives us standardized category names that are easier to analyze and compare later. We convert the unit price column from text to numeric values so it can be used in calculations. To do this, we use a Pandas function that tries to turn each string into a number. If it finds a value that is not numeric, it replaces it with a special missing value marker. This ensures the entire column has a numeric data type and is ready for arithmetic operations or statistical analysis. We create a new column in the data frame called line revenue in US dollars by multiplying the quantity column by the unit price in US dollars. This calculation gives the total revenue for each individual line item in the orders data. In other words, it shows the total sales value for each product based on how many units were sold and the price per unit. To convert revenue from dollars to cents, multiply the revenue values by 100 so the decimal point moves 2 places to the right. Then round the result to the nearest whole number so it becomes an integer. After that, change the data type to a 64-bit integer, which can store large whole numbers safely. Finally, save this converted value in a new column called line revenue cents in the data table. Finally, the program prints the transformed data table so we can review the results of our work. By looking at this output, we can check that category names have been cleaned, unit prices have been converted correctly, and revenue values have been calculated as intended. Displaying the table lets us confirm that all transformations were applied properly and that the final structure and values match our expectations. This script shows a simple example of cleaning and transforming data with a Pandas DataFrame. It starts with a small dataset of items, categories, quantities, and unit prices, then standardizes the categories by converting them to lowercase. The unit prices are converted from text to numeric values so calculations can be performed. Using these cleaned columns, it computes revenue as quantity times unit price, and then expresses that revenue in both dollars and cents. The final result is a data frame with consistent numeric fields that illustrates how pandas can be used for basic data manipulation. In this lecture, you learned to construct data frames from common sources such as dictionaries, lists of dicts, and NumPy arrays using Pandas 2.3.1. Inspect data frame structure and metadata to understand shape, columns, indexes, and basic statistics. And perform basic column and row operations, including selection, renaming, and simple transformations. In the next module, Module 2, we will go over data cleaning. Thank you for your attention. See you all in the next lecture.